All right, let's dissect this paper on improving transformers with selective attention. The authors claim significant performance boosts and efficiency gains. What's the core idea behind selective attention, and why is it significant for experts?
The core idea is elegantly simple. Allow a token within the transformer's attention mechanism to effectively ignore other tokens deemed irrelevant. This is done via a soft masking mechanism derived from a single existing attention head, adding no new parameters. The significance for us is that it directly addresses the quadratic complexity of standard attention, a major bottleneck in scaling transformers. By selectively reducing attention to unnecessary elements, we can improve performance and reduce computational cost.
So it's not about changing the architecture drastically, but rather refining the attention mechanism itself?
Precisely. It's a parameter-free modification, making it easily integrable into existing transformer models. The key is that the masking is learned, not predefined. The model learns which tokens to ignore for optimal performance.
The paper mentions several motivating examples. Can you elaborate on how selective attention helps in tasks like variable assignment and language modeling?
In variable assignment, the model needs to remember the most recent value assigned to a variable. Selective attention allows the model to effectively forget previous assignments to the same variable, simplifying the task. In language modeling, it helps the model focus on contextually relevant information, ignoring ambiguous or misleading earlier tokens that might be resolved later in the sequence. This is analogous to human selective attention, focusing on task-relevant information while ignoring distractions.
The paper highlights context pruning as a significant efficiency improvement. How does selective attention facilitate this?
Once a token is sufficiently masked, it becomes essentially irrelevant to future computations. Context pruning leverages this by removing these masked tokens from the context buffer. This directly reduces memory and computational requirements during inference. The paper employs a clever memory budgeting strategy to determine which tokens to prune, minimizing the impact on model performance.
The paper mentions an additional loss term, LLM, to further encourage context pruning. What's the intuition behind this?
LLM acts as a regularizer, explicitly rewarding the model for increased sparsity in the attention weights. It encourages the model to mask out more tokens, leading to even greater context reduction and efficiency gains. It's a simple addition, but it significantly boosts the memory savings.
The results section shows impressive improvements in perplexity across various model sizes and context lengths. How do these improvements compare to simply adding more attention heads?
The key finding is that transformers with selective attention achieve comparable or better perplexity than standard transformers with roughly twice the number of heads and parameters. This demonstrates the effectiveness of selective attention in improving model capacity without a significant increase in model size.
The paper also explores the patterns of token selection and masking. What insights did they gain from analyzing the F matrix?
Analyzing the F matrix, which represents the accumulated masking effect, reveals interesting patterns. Some layers exhibit dense attention, low F values, while others are sparse, high F values. The sparsity patterns are relatively stable across different examples and even across different training runs, suggesting some inherent structure in how language models process information.
How does this compare to existing work on attention modifications and context pruning?
Most existing work on efficient attention focuses on approximations or hardware optimizations. Context pruning methods often rely on compression or heuristics to remove tokens. Selective attention differs by directly improving the quality of attention, with context pruning as a beneficial side effect. It's a more principled approach, leading to both quality and efficiency improvements.
The paper mentions some limitations and future directions. What are some of the most promising avenues for future research?
Extending selective attention to encoder-only transformers is a natural next step. Iteratively reducing the context size during training could further improve efficiency. Investigating the application of selective attention to larger models and different attention variants, like multi-query attention, is also crucial. Finally, optimizing selective attention for GPU architectures could unlock even greater performance gains.
The authors connect their work to the art of transformer programming, emphasizing the importance of identifying fundamental problems that are difficult for both humans and current architectures. How does this perspective inform the development of selective attention?
This perspective highlights the value of focusing on fundamental limitations. By identifying a core challenge, the quadratic complexity of attention, and developing a solution that addresses it directly and elegantly, the authors demonstrate a powerful approach to improving transformer architectures. It's a reminder that focusing on the core problems rather than just incremental improvements can lead to significant breakthroughs.
The paper mentions a connection to the RASP generalization conjecture. Can you briefly explain this connection?
The RASP generalization conjecture suggests that transformers generalize well to different sequence lengths if the task can be solved by a short-length agnostic program. Selective attention, by simplifying the underlying computational process, potentially makes tasks easier to express as such short programs, thus improving generalization.
In summary, selective attention offers a compelling approach to improving transformers. Its simplicity, parameter-free nature, and consistent performance improvements across various settings make it a promising technique for enhancing both the quality and efficiency of transformer models.
Absolutely. The combination of improved performance and significant efficiency gains makes selective attention a very attractive addition to the transformer toolkit. Its elegance and ease of implementation further enhance its appeal.
This has been a great discussion. Thank you.